So there are three types of capacitors: fixed capacitor, which are not polarized, then polarized capacitor, and variable capacitors. So you can see that there are dielectric plates and insulating layer between them. So dielectric plates can hold the charge and they can store the charge. So, right, it's not moving. Okay. So the charging process of the capacitors are that if initially they are uncharged, and when we connect to some battery and resistor, they start charging, and the current start flowing until they reach their maximum voltage, which is the until they reach their maximum voltage. And once they reach their maximum voltage, they act like a voltage source or temporary battery, and they can provide charge to others, right? So they can act like an open circuit. So that's the basic operation of the capacitor. And capacitor with stored charge can act like a temporary battery. So this is another way of looking at it, that if you have a capacitor and initially you are reading a 0 volt, then when you connect the switch, you can see that it accumulated charge across it. And once the charge is accumulated and equal to Vs, it acts like an open source, and it can provide charge to other components. Then if you want to discharge the capacitor, you should connect it a low resistor across it, or if you connect resistor across the capacitor will quickly discharge. So the capacitance is the ratio between charge and the voltage, and you can also write it like this. And you know that if 22 microfarad is a capacitor and it's connected to 10 volts, the charge accumulated will be 220 microcoulomb. So the energy of a charged capacitor is given by this equation. You can calculate it using W is equals to half CV square. And where W is the energy in joules, C is the capacitance, and V is the voltage. Then capacitance of a capacitor depends on three physical characteristics, that is area, distance between the plate, and relative dielectric constant of the material between the plates. So that's how you can calculate the capacitance, because it is dependent on geometry of the capacitor. Okay. Now, so these are some practical things we will talk about. We will talk about the capacitors. So there are many types of capacitors, but we will discuss some common types, okay? So one of them is mica capacitor. Mica capacitors are small with high working voltage. They are non-polarized capacitor and fixed capacitors. Then there is a ceramic disc capacitor. They are also non-polarized capacitors. They have relatively high capacitance due to high epsilon R. Then there's plastic film capacitors. Their shape is different than the mica and ceramic disc capacitor, and they actually have a relatively high capacitance due to large plate area. Then electrolytic capacitors. So these ceramic disc capacitor and electrolytic capacitors are the common type of capacitors. Electrolytic capacitors, however, they are polarized. So they have their positive and negative. The longer lead, the longer wire is the positive, and the smaller wire is the shows the negative side of these capacitors. Okay. So then there are variable capacitors. Variable capacitors, you can change their capacitance by using their adjustable knob. Okay, so the capacitor labeling. You can see that we have done resistor coding, right? And this is available on the color coding of the resistor. In case of capacitors, you have, you can see in this pouch, you have this 100 microfarad capacitor. If you take this out, and you have another capacitor in this pouch in which you have multiple components, right? So in which there was the paper inside it, and it was a sheet which tells about the ratings or about the specification of the components you are having in the pouch. Okay, so this 100 microfarad capacitor, if you look at on the top of this capacitor, you can see three numbers, 107 and capital M. It's very small, but you can read it. 107M, right? Can you read that? Do you have capacitors with you?
Yeah, I'm just trying to get it out of the bag.
Okay. So the coding of the capacitor is, we are talking about 3-digit code. First two digits represent their value, and the third digit is the multiplier. The default value is picofarad. So here, if you can see here, 473 means 47 into 10 raised to the power 3 picofarad. Okay, similarly here it is written as 102K, which means 102 is the multiplier and K is the tolerance. Okay, so what do you think, what will be 107 equals to? If there is 107, what will be the value of capacitor?
10 times 10 to the 7.
10 and 10 raised to the power 7 picofarad, right? So it will be 1, 0, so it will be 1, what is happening here? I don't know. 107 picofarad. Okay, so what it equals to in terms of microfarad or nanofarad? In terms of microfarad, what this number will be equals to?
Pico to what?
100 microfarads.
100 microfarad, right? But what you are asking, Sam?
Never mind.
No, you can ask. You were asking
No,
how you are.
I was asking like what was the conversion?
I'm saying 107 picofarad means that you are having 1, 0, right?
Yeah.
Into 10 raised to the power 7 into 10 raised to the power minus 12, right?
Mm-hmm.
So it means 10 raised to the power 7 minus 12 makes it 10 raised to the power minus 5, right?
Yes.
1, 0 into 10 raised to the power minus 5, right? Which will make it farads, which will make it 100 microfarad, right? I don't know what's going on. Something is on this screen, maybe.
I have a question.
Yes.
For the code tolerance, what for like P downwards, what does it mean -0 to 100, -20 to 50?
Means its value can increase and decrease. So we have M, which means 20% tolerance. So we can just say that 20% tolerance means that its worst case value can be lower than 20% lower or 20% higher. That's what it means, okay? Okay, so you're good how this 100 microfarad comes?
Yeah.
Okay, so let's take another capacitor from the bag. And check the value. What is written on this other capacitor?
$106K.
106K. And how can you know what its value is?
Ten times 10 to the 6 microfarads.
10 times 10 to the 6 picofarad.
Yeah.
Okay. So what its value will come?
$10 microfarads.
Okay. Haris, what do you think? She's right?
Yeah.
What? She is right about the value,
The
10 microfarad?
capacitance, yeah.
Okay. So, but what do you think K means here?
Times 1,000, right?
No.
So it's no, sorry, it's the tolerance. My bad. So it's
10% tolerance, right?
Yep.
Okay. So we are good about this. Okay. So then we know that when capacitors are connected in series, they are opposite to what we were doing in case of resistors. So we will just do 1 over CT is equals to 1 over C1 plus 1 over C2, and how many to the number of capacitors connected in series. Then capacitors in parallel will be just addition of the capacitors, and it will be CT is equals to C1, C2, and C3 and Cn. Okay, so this is another thing we talk about capacitors in DC circuit, how they perform. So if the capacitor is charged and you close the switch and it is acting as a temporary battery, its discharging voltage and currents curve should be this. And that's how the capacitor will discharge across across the time axis. And if you are seeing what will be the charging scenario of the capacitor, so this will be the input voltage, source voltage, this will be the charging voltage, and this will be the voltage across resistor. So what is the shape of the current curve? So the shape of the current curve will be the same as the shape of voltage curve. Okay, so you can see in this shape that as the capacitor is charging to its maximum voltage, your resistor voltage across resistor is decreasing, because once the capacitor is fully charged, the circuit is connected to it. It will stop for the current to flow. But once it start discharging, current will start or voltage will start appearing again. So that's how the capacitor acts in the circuit. Okay, so this is the charging graph and discharging graph of the capacitor. One thing's there are two important things we should remember. So what is tau? What do you think? What is tau? Do you know about that?
Isn't that like R divided by C?
It's RC, not tau is RC. Yes, so it's the time constant. We call it time constant. You can see that 1 tau means that your capacitors, if you are charging a capacitor and it's 1 tau, so then it means that your capacitor is 63% charged. If you keep charging it and it reaches 5 tau, so the capacitor normally charge fully when they reach 5 tau. So this is the charging waveform of the capacitor, and similarly, this will be the discharging waveform of the capacitor. So now let's see what we have to do. So it's 15th experiment we will do. And so in the 15th experiment, we have four procedures, okay? So I will do the, what it should say, LT spice of procedure 1 to show how the capacitor should, how you should build the capacitor in the simulation and how you should do it in the practical. So we will see that. But first you have to do procedure 1, then procedure 2. Oh, and, oh, this is the wrong file, I think. Just a minute. So this is the same file you have in your, 1 minute. In the canvas, right? You don't see procedure 2 and procedure 3? In your file, which is provided in Canvas, can you see procedure 3 and procedure 4?
Yeah.
Oh, okay.
Yeah, we can see that. I have the PDF open.
Okay. So maybe I have this. Let me open it.
The PDF has it, but not the PowerPoint.
Yeah.
Okay. 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 So you have procedure 3 and procedure 4 that you have to do, and then exercise. Okay. I will start doing procedure 1. Okay. So procedure 1 is asking you to build a simple circuit with the resistor. Okay. And as we don't have in practical some square wave input voltage, we will use our normal battery with that. But for in the simulation, we will use the square wave input that can tell us how the capacitor will charge and discharge. Okay. And so we are having 10 volts in the circuit. So it's up to you that if you want to match it with your practical, you can use 9 volts too. And we will be using 100 microfarad and 1 kilo ohm resistor. Okay. So let's do LT spice first. I will do it with you. So then we will see that how we think about capacitors. Okay. Let me share my LT spice. Okay. So new schematic, I am using the resistor and capacitor. Okay. So I am saying that this capacitor is 100 microfarad, right? And resistor is 1 kilo ohms. Let's say I am saying that this is 9 volts. Okay. But here in this case, I will do advanced and I will do pulse. And in this pulse, I will say 0 is the initial voltage. Maximum voltage V on is 9 volts. And T rise is 1 nanosecond. 1 nanosecond. T fall is 1 nanosecond. T on. Okay. So this is that how much time it should remain on. So it's, let's say, we say millisecond, and let's say 1000 millisecond. Okay. Can you tell me what is RC for this circuit? What is the multiplication of R and C?
R is 10K.
No, R is 1K. So
Oh,
R
1K.
multiplies C is what?
Oh, it's it gives you one value. I mean, K is 10 to the third, and then micro is 10 to the -6. So you get negative third.
What it means?
You get micro.
Can you calculate it and tell me in seconds
Oh, okay.
what RC is? You're right, I mean. But in millisecond, what is the value?
I'm doing it right now.
Chris, do you know?
You talk about the value of RC?
R multiplied by C. It's 0.1.
Point. Yeah. Okay. Yeah, I was typing it in.
It's 0.1, right?
Yep.
So 0.1 means 100 millisecond, right? Because 1 second is 1000 milliseconds. So it means that it's 1 tau is 100 millisecond, right? So 100 millisecond and 5 tau means 500 milliseconds. So it needs 500 millisecond to charge itself. So we are good. So let's see. Oh, okay. I should add ground. Okay, so here you can see the charging and discharging waveform, okay? So you can see that capacitor is charged at about 500 millisecond to its maximum value. And then it discharged, and it took 500 millisecond to completely discharge. And similarly, as I have asked for 2 cycles, like 2000 millisecond, that's why we can see 2 cycles of the charge and discharge. So if I put my probe here, I can see input voltage, right? So this is input, and this black line is the voltage across capacitor, right? Is it good? And this is the current across R1. Is it good?
Yeah.
Okay, but let me change. If I just change the value to 250 milliseconds, what it means? What this 250 milliseconds means? Like, what do you think should happen if I am reducing the time to charge? Maxwell?
I'm not sure.
Your voice is so low. Okay, it's okay. Eric?
Could you repeat your question, please?
I am saying what will happen. So you know that what we have done, we have kept its on time as 500 millisecond and 1000 milliseconds. So, and we calculated that 5RC, 5 tau is also 500 milliseconds. So what I'm saying is, if I reduce this on time, what will happen?
It won't be fully charged.
Right? So it won't be fully charged. That's a good observation. Let's see. Okay, so see what is happening here, that we have given it a lesser time to charge, but more time to discharge, right? So it did not charge fully, but it discharged to 0 voltage. That's fine, okay? Okay, so let me try another thing. Let me give it a, so my cycle is now 500 milliseconds, okay? So what do you think is happening here?
It'll have less time to discharge, so it won't reach 0.
Yes, so it is having a less time to discharge. That's why it's not 0, and it's not having enough time to charge as well. So it's just fell short of charge and discharge both. Okay, so let's try another thing. So what is this? What I have done here.
It has more time to charge, but less time to decharge.
Yes, so it has full time to charge. That's why it reaches its maximum voltage, but it cannot discharge itself. So that's why it's just going like this, okay? So that's how you can see your charging and discharging voltage. So what will happen if I say that my capacitor value is 10 microfarad? What do you think will happen?
I feel like it should take longer for it to charge fully.
What? Repeat?
I think it should take longer to charge fully. No, less time. Less time to charge fully.
Yes, it should take lesser time divided by 10 to charge fully, right? So it's clear? This thing is clear? Simulation is clear to you all?
Yeah.
Okay, so
Yep.
now I am going to the practical thing, and I will show you. So in this experiment, I don't think you do have to do much complicated stuff. You just have to see how capacitor work, okay? So let's see. I will take 100 microfarad and a 1K resistor. I don't see what's the value here. Mix them. This is K. So this is 107 amp. Okay. So let me take the breadboard here. Oh, it's already there. Okay. So I have this 107M here. Okay. And I will do 1K across. So I will build this same circuit we have here. 1K I have. Okay, got it. Okay, so let me take 1K resistor. Okay, and I will put 2 wires across the capacitor to see the output. So this is my circuit. Can you see that?
Yeah.
Yeah.
I have connected positive terminal to the resistor's leg and negative terminal to the capacitor leg, okay? Got it? So now let me see how much time, it should take to charge itself. Like it's 100 microfarad into 1K. So how much time it should take to charge? You're not, Herschel, you're not getting a graph. Did you do op or did you do tran?
Trans, I got the graph now.
Okay, that's fine. Okay, so let me put it here and let's see the values. Okay, so can you see voltmeter, right? Now, I need to take the battery. Plug it in. Okay. So let me see the voltage across the capacitor, okay? What it is showing? Let me put my screen bigger. Just- Okay. So what this is showing? 8.9 something, right?
Yeah.
So it means your the capacitor is fully charged, right? So now I will take the resistor off. I will take the battery off and the resistor off to see that if capacitor is still charged or not, okay? So it's now, nothing is there in the circuit, okay? So it's still showing us 8.6 volts, right?
Yes.
So it means the capacitor is fully charged. But now, if I connect voltmeter across the capacitor, I am actually completing the loop, right? So it will discharge itself across the voltmeter's resistance, which is higher, so it will take time. So let's see.
It's reading 0. Oh,
No, I think I actually connected them both. That's why. No, it's fine now. Okay. Let me check. Right? Now it's going down.
0.
No, 0 is wrong. So now it's fine, right? So it is discharging itself across voltmeters resistance, right? Got it? Now, if I want to discharge it, so it's still, if the circuit is open, it will keep its charge. But now if I want to discharge it quickly, what should I do?
Connect a resistor to it.
Small resistor, small value of resistor, right? Let's check that what voltage it has across it. It still has something 7, right? So if I just short a wire across the capacitor, like, or if I just connect these 2 leads here, it will create a small path, right? And it will discharge quickly to 0 volts. So let's see once again how much charge it has on it, its terminals, okay? So it has 6.9 volts, right? Is it okay? Now let me see. Sarab, do you think it's fine? Sarab, are you here?
Yeah, I'm here.
What do you think?
Could you show us the circuit one more time, please?
What?
Can you show us the circuit one more time, like the breadboard?
Of course I can. Just a minute. So let me see that whether the capacitor discharges itself or not. Okay. So now capacitor discharges itself quickly across this wire. Okay. Which the small wire I connected across the capacitor. Is it clear now? The discharging and charging of the capacitor or not?
Yeah.
So I have not connected anything to the capacitor. It retains its charge. And if I was allowing it to discharge across the voltmeter, it was taking time. So what I did, I just shorted it with a small wire and it's discharged itself quickly. Okay, is it clear? Anybody has question? Sam, is it clear?
Yeah, it's clear.
Nicholas?
Yes.
Adeline? Eunice?
Yeah.
Okay, so let's see now. Okay, let me see now what we have to do in the 15th experiment, okay? So in the 15th experiment, this is AC one. Okay. So in the 15th experiment, you can see that in the first procedure, what you have to do, you need to connect a capacitor with the resistor and the voltage source, and you can see that you need to calculate the steady state voltage. Steady state voltages are which you get when the capacitor is fully charged, okay? So then you have to record current, I, voltage V1 and V2. So if you are using a DC source, what do you think will be V2 at the steady state? In our case, it was 9 volts. So what we have seen across capacitor, what voltage we have seen across capacitor when we connected the battery? I'm talking about the B part. So we saw 8.9 volts, right?
It should be like whatever the voltage is of our power source.
Yes. So it will be almost 9 volts across the capacitor. Okay. And V1 will be 0 because there will be no current flowing in the circuit once the capacitor is fully charged. Okay. So that's what it should be in this experiment. And then that's what you can see in the simulations too. Okay. Then you can calculate energy of the energy stored by the capacitor by 1/2 CV square. Disconnect the supply and measure the voltage across the disconnected capacitor. Is there a reading and why? That you can do. Short the capacitor terminals with a lead and then measure VC again. Okay. So that's the one part of it. The other, in the part 2, you can see that we have a circuit that is, there are 2 resistors across it, right? So the circuit will be like the voltage that will accumulate across the capacitor will be the voltage that will be appearing on V2. So think about it that once the capacitor will be open, I am talking about procedure 2. Okay. Let me share my screen again. So in the procedure 2, once the circuit will be open, the voltage across V2 is the same voltage that will appear across VC. So V2 is R2, this is the divider circuit when the C is open. So it will be R2 divided by R1 plus R2, and whatever the voltage here will be the voltage that will accumulate here. And what do you think, once the capacitor is open, what current will be flowing in the circuit? Will any current flow in the circuit? So once the capacitor will be open, only I1 will flow here, right? And this current will not flow in the circuit. Can you see the mouse?
Yeah.
R2 would be shorted, right? To start out.
No. So what will happen? So once you have connected a battery, current will flow here and here, right? But the voltage here should remain the same. So the voltage, what I'm saying that whatever voltage supposed to be here is the divided voltage that you will get here. So the VC will be that voltage. Once it accumulates this voltage here, this circuit will be disconnected because it accumulated the equal voltage and it will be acting as an open circuit. Only this current will be flowing in the circuit. So to measure the current, you can just connect your leads here and see that whether the current is flowing even after the capacitor is discharged. You can also see the current here. There should be no current here, okay, in this branch.
So when does it, I have a question.
Mm-hmm.
So it charges, and because of that, it has no current, and so that no charge flows. But when does it discharge? Because it's also connected to resistor too. So when does it?
Yes. So it will not discharge until you have a battery here, right? So once you disconnect the battery, it will discharge itself across this capacitor, across this resistor. This circuit will open once you disconnect the battery, and the capacitor will discharge across this resistor, and the current will start flowing in the opposite direction. Okay?
Oh, all right. I get it. Thank you.
Because capacitor will start acting as a battery.
Once you take out the existing battery source.
Yes.
All right. Gotcha.
Got it? We are on the same page in literal meanings and in other meanings. You all got it? Benjamin? Okay, so let's move to procedure number 3. Okay, so in procedure number 2, you have to just do the currents and voltages for the steady state values. Okay. Okay, so procedure 3.
Wait, so we don't have to worry about when it first starts up, just once, like you said, just steady state.
Yes, we are just doing steady state here.
Okay. And then for when we build these, like what should we use as our R2 value on our breadboard, since we don't have a 3.3?
You don't have 1K ohms?
We have 1K. Oh, okay, so you just want to use two? We'll use two 1Ks.
Oh, yeah. It's okay.
Okay.
Yes, you can just use 1K. Yes.
Okay.
Okay. Okay. Yes. So here, this is interesting. What should happen in this circuit? Once the capacitor will charge itself, both the capacitors will charge itself, what should happen? Is there any current will flow here?
Once they're fully charged, there shouldn't be any current flow.
Yes, there shouldn't be any current because they don't have any alternate path that has a closed loop in it, right? So there shouldn't be any current flowing in the circuit once they C3 and C2 are charged fully. Again, you can use 1K ohms, it's okay. And then once you disconnect the battery, the capacitors will discharge themselves across this resistor. Okay, until and unless you close this path with some, wire or something. Because this path is open, so the capacitors will charge themselves here. Okay.
I have another question.
Yes.
If the polarity of the capacitor was reversed, would it also wait until the energy, the battery source is removed, or would it just act as another voltage source?
So right now, the capacitors we have, they don't have polarity, but the polarity comes with the direction of current, right? So as the current is flowing in this direction, so they accumulate the charge according to the charging current's direction. Okay, so once they disconnect and they want to discharge themselves, so of course they have this as a discharge thing, so they will discharge themselves in the opposite direction. Got my point?
Yeah, I understand. The question was if, like, for example, the capacitor was negative to positive in the circuit, would that type of like circuit not work, or would it be able to just act as a voltage source? You get what I mean?
No. If the battery is there, how it can work in the negative direction?
So you won't be able to put a capacitor, reverse the voltage and make it, and the circuit.
No.
Okay. All right.
Because the capacitor doesn't have any polarity by itself. It just develops the polarity with the voltage source.
All right, makes sense. Thank you.
Okay?
Yeah.
Okay. So this procedure 4, I think in the procedure 4, you are given capacitor that is 100 microfarad, but you need to calculate this value. One thing you need to see that in this procedure, you have 100K and 100 microfarad. So both values are different. Why we are given the higher values? So that we can see charge and discharge, because the time is increased now, okay? So they want you to charge the capacitor and record the time that it reaches the 63% of its value. So like here they have 10 volts and the 63% of 10 volts is 6.32. So you can just check the 63% of 9 volts, right? And then you want to see how much time it will take to reach 63% of 9 volts. That will be 1 RC or 1 tau. And from there, you can calculate your capacitance, okay? So I want you to do procedure 1 and procedure 4 first to get yourself familiar with the capacitors, and then you can move to procedure 2 and procedure 3, okay? So is it clear?
Could you go over again how you would calculate your capacitance using the multimeter?
Oh, so we did not, okay, 1 minute. Angeline, can you hear me? You're saying you have a problem hearing me?
Yeah, it sounds kind of muffled. I was gonna leave the class and come back if that's okay. I don't know if it's
Or
my
is it my voice is too high? Is it good now?
It just sounds muffled. Like I hear you just a little bit.
Okay, yes, you can connect again.
Okay, I'll be right back.
Okay. Okay, so what I was showing you here, that we were not calculating capacitance. We were seeing the voltage across the capacitor, right? Or we cannot calculate capacitance using this voltmeter we have. There are LC meters which can help us to calculate capacitance, but with these voltmeters we can just calculate. We can just see the resistance. We cannot see the capacitance. So the procedure 4 is asking you to see the capacitance, which they want you to do like this. 1 minute, I can show you. So, no, not this. So here, if you see that I am seeing you that in procedure 4, you have to do this. Let me see. So you have to calculate RC, right? RC is tau. And tau is 60. So in 1 tau, in this time, the capacitor charges itself 63%, okay? Which means that if you are giving it 10 volts, it will be charged to 6.3 volts, right? So once you have this 6.3 volts, what you can do, you can take that time and divide by your R. That will be your value of C. Okay? In procedure 4. So you need to record the time using your stopwatch, that how much time capacitor takes to reach this value. Okay? That time you are saying that is 1 tau, and then divided by your resistor, that is 100K, and then this will be your capacitor's value. Okay?
I understand.
Okay. So I think that's about it. You can start doing procedure 1 and procedure 4, and I'm here. You can ask me any questions, okay? Are we good?
I have a question. So we're using the 9 volts for all of them?
Yes.